Okay, so while laser is operating at this in the scale, you can observe. So it's actually in steady state because the interaction time of the electron and the carrier is in the nanosecond level. So if you can observe that, it's already pretty long for them. So we can always find a small part which is steady state. Then we can equate both the ray equation for electrons and the carrier to be 0. So let's taking the ray equation of a photon for example. So dNp over dt is gamma times Vg npg plus beta sp times rsp minus np divided by tau p. When it is equal to 0, we can put the positive one side, negative one side. And while lasing, so this is tricky. If we don't make this assumption, you will definitely get still a pretty smooth curve, but that will be relatively difficult for you to do it by hand. The merit of doing it by hand is that you will actually have time to consider by your own brain, not to just put it into a simulation software and try to read the result. Okay, anyway, so in order to simplify that, let's consider it's already operating in the laser region. So we can neglect this part because now the stimulating emission is taking control. Okay, so we neglect the beta sp rsp first. So and it equal to 0. So gamma Vg times npg should be equal to np divided by tau p. Then we can divide it by the np here and here. So we have the gamma gth is equal to 1 times divided by group velocity times tau p. Why do we write down a th here? That means it's already in its threshold condition. Threshold condition is the intersection between the spontaneous emission and stimulating emission. Although it should be a continuous curve, but there will be something like we can call it 拐点 or like some turning point, like it obviously from spontaneous emission to stimulating emission. So such threshold level we can denote TH threshold in the subscription. Okay, so we have gamma GTH threshold gain should be 1 divided by Vg divided by tau p. Okay, so this is a threshold condition. But this is correct but not useful because who knows what the tau p is? Tau p is just a term to help us to write down the carrier, the photon consumption in the cavity, but we really don't know what the tau p is. So we need to working harder to replace this term by other equations. All right. So in this case, the GTH is called threshold gain, and when G is less than GTH, it is not lasing yet. But when G is higher than GTH, okay, that will be another story. I don't want to make a judgment first. Anyway, since the photon density is now under steady state, that means the mole profile shouldn't change with time. So let's consider an optical mole, cross-sectional, measure U of x, y. And let's start from arbitrary point. Okay, so for convenience, just let's start it from the mirror 2. Then it propagated toward mirror 1. So first, it will be U of x, y times, okay, let's start from mirror 2 to mirror 1, times exponential I beta L. Okay, well, okay, I will do this. This is mirror 2. And I have a photon optical mole file going from right here. So from here to here, and the net gain is gamma G minus alpha. This is quantum wave, and it has gain. But the other part might have loss because of scattering or free carrier absorption anyway. So in average, the net gain will be gamma G, but the absorption will be an average the loss, because there will be probably this is alpha 1, this is alpha 2, every layer has a different alpha. So we need to make net loss. So times L, because it propagated L length, then it becomes U of X, Y. So in this case, it might be stronger, for example like this. Okay. So while light propagating from 0 to 0, 1, here it becomes Ux, Y should be, let's call it Us 0, should be Ux, Y 0 exponential I half of gamma G minus alpha. This is the net gain or loss, because this is electric field. While we are doing the intensity, we will need to take a square. Then it will be gamma G minus alpha. But now it is only field, so we need to divide it by 2. Okay, L. All right. So then the field is reflected, because it is a surface, it is some reflectivity. So that's called R1. Okay, so because the reflectivity is less than 1, then the field might be a little bit less. But it is gaining again, so become larger again. Okay, then make another reflection, R1. Alright, so after a round trip, it becomes U of xy times R1 and R2 times exponential I beta to L, because you have a traveling L twice, and the beta is half of gamma G minus alpha, the average, the loss of your laser structure. Oh, sorry. This is only sorry, I withdraw that, but this is not gamma. So this is only the phase term. This is the beta is lambda 2 pi NEFF. The effective refractive index. This is the phase term. So beta, okay, beta times 2L. And the gamma G minus alpha also, because this is only L, but you will do it twice, so it's 2L. So it finally becomes 2 and divided by 2. So there will be gamma G minus L. Okay. And after one term, because it is steady state, it should be equal to its original intensity. If it is not, the electric field here is gaining its intensity. Then it is not a steady state. So what we get steady state, that means it don't change with time. So the same optical profile going one round, it should return to its original intensity. So we can write it down like this. Okay, so it should be original u of xy. Then you can divide it the original term at both sides. So this is the generalized implant laser, which might contain the active part with quantum well or with active region, passive part with no active region. And how do we calculate the internal loss? Let's consider a simple SCH laser, something like this. This is the refractive intensity. And after some calculation, probably the fundamental more like this. This is electric field. Then this layer might have an absorption value. For example, this might be alpha 1. This layer might be alpha 2. This layer might be alpha 3. Then the portion of the electric field, gamma I, when it is not in the active region, we can call it overlapping function. If it's in the active region, we call it confinement factor. That's the same thing. So gamma I is calculated by the integration of E squared dV in all layers, all structure, divides layer I, just this part, so E squared dV. Then the loss, average the loss, is surely equal to gamma I, alpha I, sigma or I. For example, in this case, this part might be 2.25, and the symmetric, so this part also 0.25, and the middle part probably is 0.5, something like that. Yeah, the summation definitely should be equal to 1. Then you can calculate the total internal loss, layer by layer. Okay. Alright, so in order to achieve the same profile after round trip, we need to consider two things. First is its phase. It needs to return to original phase. If it is not, it will be destructively cantilevering of itself. So the first is that the phase should be consistent, and the second term is that the intensity also need to be consistent. Okay, so now we have the complex propagation constant like this. Beta should be, beta, how do I say that? Wave? Beta plumb? I don't know. Okay, so we can have beta with the real part and the imaginary part. The real part will be relevant to the phase. It will be K0, the wave vector in the vacuum, times its effective refractive index of a specific mode. That will be 2 pi over lambda. So while doing up lots of mode simulation, you are actually finding this number, because this is a value from the vacuum. So the number of NEFs is the solution with the thing we want to calculate in many times. Okay, anyway, this is the term dominating the phase. Second, we have the beta I, the imaginary part, dominating the intensity. So it will be 1 over 2 gamma G minus alpha. The net gain divided by 2 because this is only electric field. For intensity, you need to take square. Alright? So after run to R1, R2 times exponential 2j beta ALA, exponential 2j beta PLP should be equal to 1. Then we can do log at both sides. What do we get? So we can divide the R1, R2 to the other side. Then take a log. Then take a node, we can only return within. So you have a gamma xy times ALA and the alpha B LP. Because the passive term don't have a gap, so it only has the alpha B LP. It doesn't have any gap. It's equal to natural log 1 divided by R1, R2. Then we can make alpha the minus term to the other side. Gamma xy times threshold gap times the length of active region will be equal to the alpha ALA plus alpha PLP plus L natural log 1 over R1, R2. Then we can divide it by the L at both sides. Then we define the actual confinement factor as LA divided by L, the portion of length which is active. Then another gamma, the overall confinement factor as gamma xy, the cross-sectional confinement factor times gamma z. And the alpha ALA plus alpha PLP further divided by L is just like do another weight, 权重, again. So this will be the total modal loss. We have the term modal loss because this depends on the mole profile. Because the optical mole may be stronger here and there will be different between different modes. So this value will depend on the mole profile you have. So we call it modal loss. Similarly, this term is called the modal gain because it is a weighted optical gain to a specific mode. Just like the midterm says, why does the TE201 is not TE10 mode is not accurate? Because its optical confinement factor is pretty low. Yeah, but I don't expect you to give a so specific answer. So you can say that, oh, we have a strong carrier intensity in the center, but for the TE10 mode, it is a no. Yeah, I will give you a full credit. Anyway, so this is the modal gain. This is the total modal loss. And the rest term, 1 divided by L times log 1 divided by R1 and R2. This is the loss, the optical energy loss, leaving the cavity. So we can call it the mirror loss. So the whole term becomes a very elegant statement. Gamma GTH should be averaged alpha plus alpha n. In English, while the laser is in its threshold condition, the modal gain should be equal to the modal loss times plus the mirror loss. Or a more simple way, while the laser is operating or functioning, the gain provided by quantum wave need to overcome all loss caused by the cavity. Or gain is equal to loss. That is the rule of thumb of the semiconductor laser. How do you have a low threshold gain? You must reduce its modal loss and the mirror loss. Then we can further decompose how does the modal loss come from, where the mirror loss come from. how do we confine the electron in the cavity stronger and stronger? What can you do? By what design? Yeah, so that will be a very huge problem with a very huge issue with a pretty simple statement. So while we're writing down this, it doesn't limit it to the very parameter type. In this case, we consider the cavity with two parallel mirrors, and the field is bouncing here and back. But it doesn't. This is a specific case. Today, it could be a periodic air hole. It could be an interface between the metal and the dielectric. Or it could be a range, a lot of nanopillars. The light is going and scattering here and back. The lacing criteria is the same. How does it lace? It laces when the optical gain or modal gain provided by your active region could equate or could be the same to the loss absorption by its material and the energy leaving its cavity. While these two terms balance, the semiconductor will lace. Okay, so it's a pretty